We're trusting AI with so much these days, driving our cars, spotting malware, even helping out in surgery. But what if these incredibly smart systems have these, well, hidden blind spots? We're talking about vulnerabilities so strange, so alien to how we think, that they can be tricked in the most bizarre ways you can imagine. Let's dive right in. This quote right here, it really hits the nail on the head. It highlights this huge gap between the kinds of attacks that are created in a research lab versus the actual threats that exist out in the real world. So today, we're going to explore this fascinating art of deceiving AI and the incredible challenge of defending it. Okay, take a look at this. To you and me, it's a toy turtle, right? But to a state-of-the-art AI, it is, with almost 100% certainty, a rifle. And it doesn't matter what angle you look at it from. That specific texture on its shell is like a secret code that just completely and utterly fools the machine. Or how about this one? Researchers proved that just a few pieces of tape, what just looks like a bit of graffiti to us, could totally trick the AI in a self-driving car. Suddenly, the car doesn't see a stop sign anymore. Nope, it sees a speed limit 45 sign instead. Wild, right? So what in the world is going on here? This isn't just some clever party trick. It really makes you stop and ask, how can a technology be so powerful, yet at the same time be this fragile? And maybe more importantly, what are we going to do to fix it? To answer that, we really need to pull back the curtain a little bit. Let's take a look at exactly how these so-called adversarial attacks actually work. You see, it's not magic, it's just math. What these attacks do is add a very carefully crafted, often totally imperceptible, layer of noise to an input. This noise is specifically designed to just nudge the AI's decision-making process right over the line, forcing it to completely misclassify what it's seeing. Yeah, this is a great way to think about it. For an AI, an image is just a massive grid of numbers. An attacker basically finds the perfect typos in that grid that, while being totally invisible to you and me, completely change the image's meaning to the computer, turning a panda into a gibbon, or, a turtle into a rifle. And this is not just random guesswork. There are clear recipes for this kind of deception. Methods like the fast gradient sign method, or FGSM, essentially calculate the single most efficient way to change an image's pixels to cause the most confusion for the AI. It's incredibly precise. And this vulnerability isn't just about what AI systems can see. The exact same principles apply to what they hear. You can hide inaudible commands in audio files, or you can apply it to how they analyze software, making a dangerous virus look totally harmless to an AI detector. But, and this is a huge but, this brings us right back to that quote from the beginning. Here's the crucial point. These attacks are way, way harder to actually pull off in the messy, real world than they are in a pristine lab environment. I mean, think about it. Attacking an image is one thing. You can pretty much change the pixels however you want. But attacking, say, a network security system, that's a whole different ballgame. Network data is incredibly rigid and constrained. You change the wrong bit in a data packet, and the whole thing might just fall apart and not work at all. And this slide really shows the core challenge for an attacker perfectly. Look, you add some noise to a picture of a cat, and you still have what looks like a cat. But adding noise to a piece of malware, well, you run a very high risk of breaking the very malicious code you're trying so hard to hide. The attack just fizzles out. So this gap between the theory and the reality, it's actually kicked off this fascinating arms race. Researchers aren't just trying to patch these little holes, they're trying to develop fundamentally more resilient and smarter AI. And you know what? One of the most powerful defenses is, surprisingly, pretty simple. Just constantly retrain the AI. An attack that was perfectly crafted for today's model becomes stale and useless tomorrow because the model has already learned from new data. It's a constantly moving target. And the data on this is just crystal clear. Look at this. An attack on day N dropped the model's accuracy all the way down to about 75%. But the very next day, after it was retrained on new data, that attack was basically useless. The accuracy shot right back up to nearly 94%, and then even higher the day after that. Okay, so making attacks harder is great, but it's not enough. The real holy grail in this field is something called certified robustness. We're talking about a mathematical guarantee that a model's prediction is correct and that it won't change no matter how an attacker tries to mess with it, at least within certain limits. A technique called pixel DP basically creates a mathematical shield around the AI's decision.
It calculates a safety zone around its top prediction. And as you can see here with Panda, if that red and green zone doesn't overlap with any other possible answer, the model can actually certify its own answer as robust. It knows it can't be tricked in that specific instance. It's brilliant.
So, after this whole tour of the digital cat and mouse game, what does it all mean? Where do we possibly go from here?
Well, ultimately, these vulnerabilities don't mean that AI is broken. Not at all. What they really signal is a brand new, high-stakes frontier in cybersecurity. We're being forced to build AI that isn't just powerful, but is also genuinely resilient and trustworthy.
And the road ahead is honestly pretty exciting. Researchers are working on AI systems that can automatically defend other AI systems. They're looking at building security directly into the silicon chips themselves. And some are even searching for a unified theory to understand this entire field. It's a fundamental shift in how we build intelligent systems.
And this really brings us to the final big question. This whole field challenges us to ask not just what our AI can do, but how it actually perceives and understands our world. So as our creations get smarter and smarter, how do we make sure that they also get wiser?